So let's go on and talk about survival analysis. I will just give everybody 1 minute or two to read this so that we can, discuss a little bit about the terms before we go on and talk about the R codes. Nolu, are you with us now? Looks like Nolu dropped off. Okay. Okay, great. So I'm assuming that you've had a chance to read it. So in 2009, you conducted a study among resident doctors asking about their workload. Every year for 10 years, you return to the same group of doctors and ask if they're still practicing clinical medicine. If they've stopped practicing, you ask them when they stop and you recorded the date in month and year. So what's the time origin of the study? Anybody can just unmute themselves and speak.
2009.
2009. Thank you, Z-Book. Any other thoughts? Is there anybody who thinks it's a different year? I agree that it's 2009. So what is the target event?
That would be stop practicing.
Stop practicing clinical medicine.
Yeah.
Great. What's the time scale?
10 years.
10 years.
The time scale is 10 years. Any other thoughts?
Every year, since it's the duration is the 10 years, but every year they will followed up every year to check whether they are still practicing. So the scale should be 1 year.
Yeah, I would think that the scale is 1 year. So when does administrative censoring happen in this study? Do you remember the discussion about censoring? When is this study censored administratively?
Should we say 10 years? That be 10
Yeah,
years?
I'll say 2019 because from the information we have, it says every year for 10 years. So it looks like it was done for a period of 10 years and everybody got censored at the end of 10 years, which would be 2019. Okay, give an example of a reason why a practitioner ignored this patient. Give an example of a reason why a doctor may be censored before the end of follow-up in this study. Is there any example, any reason why somebody may be censored before the end of the study?
Maybe, hello?
Hello?
Maybe the person possibly changed the facility. Maybe he moves from the facility where the study is being conducted to another facility, in that he cannot be accounted for. So just like drop out of the study.
So if they were lost to follow up.
Yes,
right?
lost to follow up.
Okay. Any other thoughts? What else do you think could happen? Maybe
they
yes,
passed
please go
on.
on, Zibo.
Maybe they passed on.
Yeah, maybe they died. So those are examples of reasons why people participating in the study could be censored before the end of the study. Okay, so now let's talk about Kaplan-Meier plots. Like you learned in class, Kaplan-Meier plots are graphical representation of the survival function. And basically the survival is just, the percentage of subjects who have not had an event at a particular point in time, depending on what the event is. So in this, here we are going to load the survival package. So library survival, and then we're going to ask R to plot the survival graph, to plot the Kaplan-Meier plots using this subfit command. And then we are specifying our parameters here, the month where they switched and whether they exited, yes or no. Remember that in time to events data, there are two things that are really going on in that data: whether the event happened, yes or no, and then how long it took before the event happened, right? So the switch MOS, switch underscore MOS, is how long it took. I'm just explaining what's in the data that we all have. And then the exit is whether it happened, yes or no. And then this is the data. We're asking mark.time equal true is just asking R to like put a vertical mark when people are censored. And then here is just the label, x-axis label and the y-axis label. So are we good with this?
Sorry, please can you go over this plus survival bit, this switch months exit?
Okay, so here's what I'm going to do actually. I'm taking us back to view RDS. Can you see the RDS data frame, or are you still seeing the code?
Yes.
Yes.
Yes. I see.
Data frame.
Yep. You can see the data frame, fantastic. Okay, so this is the variable called exit. Remember that here we're saying, did they exit clinical practice? Did they stop practicing or not, right? So this is the variable or the column called exit, and it's either 1 or 0. They either stop practicing or they did not stop practicing, right? And then the switch month is the time that it took them to either stop practicing from 2009 that we started collecting the data, and we started asking them which month, what proportion stop practicing in the first month, month 2, month 3, like that. And then so these are the two pieces of data that are in our survival analysis: whether the event happened and how long, the time to the event happening, either time to the event happening or time to the end of the study, because things could happen after the 10 years, right?
Okay.
Abbas, does it make sense now?
Yes.
Okay, so basically these are just what's it called? These are just the variable names in our data set. And so basically we're asking R to fit this, to say this is our survival function. This is how long it takes. This is a time to the event, and this is the variable that tells us whether the event happened or not. Are we ready to run it?
Yes.
Okay. So this is what the survivor curve looks like, right? What do you think these are? The dotted line, the dotted lines. You can see two dotted lines and one solid line in between. So what do you think the dotted lines are?
Confidence interval.
Confidence interval. Yeah, thank you. Okay, so this is what the this is the Kaplan-Meier curve. And you can see that at time 0, this is months, right? At month 0, the event had not happened to any one of them, right? So the probability of the proportion who had not experienced the event was 0. It was 1 at month 0. And then as time went on, you can see that more and more people were experiencing the event. And let's go to then out. I think it'll be clearer in the next one. Okay, so the one we had before, it had the curve itself, and then the 95% confidence interval, which can make things a bit crowded. So you can decide, you know what, I don't want to see the 95% confidence interval. And another thing that you can see here is the Kaplan-Meier curve. Everything is just like almost pushed to the top of the chart, right? You have all this dead space. Oh, you can't see. You have all this dead space at the bottom, and the chart is really just like pushed to the top of the curve itself is pushed to the top of the chart. So you can change all of that, or you can modify all of that using this, using a few arguments. So here we're still doing the same thing. We're asking R to plot the survival curve using the same two variables, the same data, RDS. Now we're suppressing with conf.int equal false. We're suppressing the confidence interval. Don't show me the confidence interval. And then x-axis label, y-axis label, we specify it. And then we can specify the limits of the y-axis. Instead of it going from 0.0 to 1, we're saying just go from 0.6 to 1. It doesn't change the survival curve. It doesn't change the data. It just changes the interval of your y-axis. I think running it and showing it will make it clearer. So can you see that the y-axis now runs from 0.6 to 1.0?
Yes.
Instead of running from 0.0 to 1.0 earlier. And now the survival curve itself is not so pushed to the top. You can see it more clearly. And of course, it has now suppressed the 95% confidence interval lines. So what do we see here? This looks a bit clearer. So what do you see here?
From the graph?
Yes.
It's like people begin to drop out of the study at around month 17 or so.
So great.
Stop practicing clinical medicine at around month 17. So each step is indicating that there is a drop. So and the probability or the proportion of those that are remaining in the study is becoming less.
Yeah, and you can see that, like earlier in the study, there were not too many, the drops were kind of like far out, but towards the middle of the study, it was like events were happening. For instance, if you look at like month 30, from month 30 to month 60, the events were happening very rapidly. And then of course, like Abbas said, as the events happen, the number of people left in the study becomes smaller and smaller. And so the events are a bit more stretched out. The time between events are a bit more stretched out. So basically, this is the Kaplan-Meier curve, and you can calculate many other things from here. You can ask R to show you the proportion that happened at whatever month. You can ask her to show you the median survival time and all of that. Do we have questions about this, how we got here?
Not from me.
Okay. Thank you, Zibo. Let me see. Who do we have? Who else do we have on the call? Mahmuda, Oziama, do we have questions about how we got here?
No.
Okay, great. So in that case, I am going to move on. So the first two curves that we did, they were just overall. This is what happened within the study population. We can actually also just compare groups. So say what happened, how did this differ, or how did this differ between men and women, for instance. So for the next activity, we're going to stratify the participants by their gender. So we're doing similar things. We're calling up the survival library. We're asking R to plot the survival to fit the survival function. We've specified our the time to the event and the status of the event. Then earlier we were saying tilde 1 because we didn't stratify, but now we're going to stratify by gender. And then we still specify our data, the name of our data. We're asking it to mark the time where people are censored. We're asking R to suppress the confidence interval. And then we're bringing in legend, because how do you know who's male, who's female? And these are the colors for the legend. There's a R library of colors that tells you the numbers and all of that. We still tell it, this is what I want you to name the x-axis, the y-axis. This is what I want the limit of the y-axis to be, like we said earlier. And then these are just aesthetics to specify what the legend will be. So this is the coordinate of the legend. Think about coordinate plane, where we want, Zbook, I see your hand, just give me a minute. So the coordinate is where we want the legend to be. Then the names of the legend, the colors, and then this is a line type. Zbook, please ask your question.
Okay, yes. At the gender, tilde female.
Yes.
Is it, let's say for instance, now we have two genders. So once it's not female, we assume it's male.
Absolutely.
So could that refer to a column that is just specified gender? That's what I'm asking.
Why don't we go into the data set and take a look?
Okay.
So can you see this column? Column 8.
Okay.
So gender in this data set is just specified as female. So female 1 or 0.
Okay.
It's just a characteristic of the data. That's how it was named. Maybe, another set, maybe another data set, they would say, maybe 1 or 2. 1 is female, 2 is male. It's just the way the data was set up.
Thank you.
You're welcome. Okay, great. So can we go on and run this? Do the arguments in this set in this lines of code, do they make sense? Do we understand that? Okay, so I'm just going to run it, and then we'll see if we have questions after. So now you can see that we've stratified this Kaplan-Meier curve by gender. The blue is the female, the red is the male. So does anybody want to tell me what they think, what they see here?
The dropout rate for males was higher than the females.
I agree with you. How did you get to that conclusion? Looking at this.
The stepwise movement, especially from about the 15th week thereabout, there seems to be more steps dropping out than the females that occurred after the 20th week, and it continued in that order all the way.
Okay. Yeah, looking at it, you can say, yeah, it looks like there's definitely looks like there's more activity in the male curve than in the female curve. At the same time, you can also just look at the probability that the event has happened per time. Look at month 20, for instance. If you look at month 20, the probability that people dropped out of practice, for male, it's probably about 0.98. For females, it's still 1, right? And then if you take the probability at 60 months, what is the probability that people are still in practice? You can see that for males is about maybe 0.85, but for females it's still much higher. So you can just looking at the proportion, just looking at every point in time, the proportion of participants who had not experienced the event looks like there were more females who had not experienced the event than males. So I would agree with your conclusion that it looks like males dropped out more than females.
Thank you.
Do we have questions? Okay, so I'm just going to move on. Here, it talks about including the confidence intervals, because like when you look at what we did before, yeah, it describes the population and says, okay, this is what's happening in this population of doctors that we looked at, that we studied. But if we want to be able to make inferences to the general population that these doctors represent, then confidence intervals will help us. So here, what is different? It's the same set of codes that we ran here, but now we're no longer suppressing the confidence interval. So we're saying, we're calling the survival library, we're asking R to plot it to fit the survival curve to this survival function. We're still saying our predictor is gender. This is the data that we're using. It's marking time to show us when censoring events happen. We're now asking R to show us the confidence interval. And all these are arguments for the legend and the chat. So this is the x-axis label, y-axis label, the limits of the y-axis, and then what we want to name the coordinates where we're going to place the legend in the chat, the names, the colors, and the line type. So let's run it and see. So can someone tell me what they see here? Hello, any takers?
Yeah, but it's so busy.
It's very busy, okay?
Okay. Hello.
Hello, Abbas.
Yeah, I can see that there are like two sets of confidence interval. The dotted line that are arrayed, the lower, it's in the one at the bottom is indicating that the lower boundary of the confidence interval, and then the dotted line that is arrayed for males, sorry, the confidence interval for males is the dotted lines that are colored red, those below the red line and above the red line. And also for females, the confidence intervals are the dotted lines that are colored blue.
Absolutely. You're right. Thank you, Abbas. Also, like Z-Book said, it's very busy, and you can see that there's like overlap, right? You can see like the lower confidence interval. If you look at for female, the lower confidence interval range for the female is overlapping with the values for the male. So it's not, when you consider the confidence interval, there's not like a really clear-cut difference, right? We can use ggplot to make this even prettier. So we're calling the survival library, we're calling the ggplot2 library, we're calling, the package, we're calling the ggfortify package, and then we're basically assigning that this is the name of our plot, and it's the same thing, right? We're asking it to fit the survival curve, and this is our survival function, this is our data, and then we're calling all this autoplot. This is the name of the object that we created. This is the y-axis limit, the x-axis limit, and then we're saying this is the name, this is the label of the y-axis, this is the label of the what's it called, the x-axis, and then the theme that we're giving it is a theme underscore BW. It just gives us a prettier and, if you like, more intuitive chat, right? So what do we see here?
Okay. It has now colored the confidence interval.
So it's basically colored the confidence interval, you're correct. But it's a bit, I don't know about you, but for me, it's a bit easier on the eyes to see and to like begin to think about, okay, I can see this area. Can you see where my cursor is? Not exactly.
Yes.
Oh, okay. Okay, great. So, I can begin to say, for me, I can begin to say, okay, I see this area and I can see that there's some overlap here, right? And so you may want to, when you see this overlap, what comes to your mind with respect to maybe statistical significance or significant differences? What comes to your mind here? Oops, sorry, I shouldn't have done that. Okay, so when you see this stratified Kaplan-Meier curve with overlapping 95% confidence intervals, what do you begin to say? What do you begin to think? Oziama, what do you think?
Not sure right now, sorry.
Okay. Okay, so personally, when I see this, I'm like, yeah, the curves themselves, I can see that, the male curve is lower than the female curve, and it looks like the males had more events than the females. But is this really statistically significant, especially with this overlapping 95% confidence intervals? I am more likely to say, no, I don't think so. But